Right now, at this exact moment, there is a small machine drifting through absolute darkness roughly 15 billion miles from where you are. It weighs about as much as a grand piano. It was built by a hand in a clean room in Southern California nearly 50 years ago by engineers who are now mostly retired or gone. Its power source, a few cylinders of slowly decaying plutonium, generates less electricity than a standard household light bulb, and it is the farthest thing humanity has ever sent anywhere. Voyager 1 does not know it is alone. It has no awareness. It carries no artificial intelligence, no onboard decision-making beyond the most basic fault protection routines. It is, in every meaningful sense, a message in a bottle. Except the bottle is moving at 38,000 miles per hour. The ocean it travels through has no shore, and the message it carries includes the sound of rain, a mother greeting her newborn child, and a piece of music by Chuck Berry. If you were standing next to it, which you cannot, because the space around it would kill you in seconds, you would see something unremarkable, a white dish antenna about the width of a small car, a boom extending outward with instruments at its tip, a golden disc bolted to the side, etched with diagrams that explain, in a language of mathematics and pulsar positions, where Earth is. The whole thing looks less like a spacecraft, and more like something you might find in a university science lab. Ordinary, unimpressive, built from parts that a modern smartphone would outperform without effort. There is no sound where Voyager is. Sound requires a medium to travel through, air or water or solid material, and the space between the stars contains so little matter that for all practical purposes it is a vacuum. If you could somehow float beside the spacecraft, you would hear nothing. No hum of machinery, no creak of metal expanding or contracting, just silence so complete that it would press against your ears like a physical thing. The only signal Voyager produces is electromagnetic. Radio waves beamed toward a planet it left behind half a century ago, aimed with a precision that allows a dish antenna in the Australian desert to pick up a whisper broadcast with less power than a refrigerator light bulb from 15 billion miles away. And yet this ordinary machine has done something that no other object created by human hands has ever done. It has left, not just the neighbourhood, not just the block, it has left the entire sphere of influence that our star projects into the galaxy. The vast bubble of charged particles and magnetic force that the sun breathes outward into space, and it has crossed into the medium between the stars, the actual space that separates one sun from the next. It is out there, right now, drifting through material that was forged in the furnaces of stars that died before our own star was born, and recently it found something no one expected. The word found carries a certain weight that is worth being careful with. Voyager 1 did not turn a corner and stumble upon a wall. It did not photograph a strange object hanging in the void. It cannot see. Its cameras were turned off decades ago. What it did, in its quiet, methodical, instrument-by-instrument way, was register a change, a shift in the numbers. The magnetic field around it grew stronger. The density of the charged particles surrounding it increased. These are not dramatic events in the way a human mind craves drama. There was no flash, no alarm, no sudden spike on a screen while a scientist gasped. There was simply data, transmitted at the speed of light across a distance so vast that each packet of information takes more than 23 hours to reach Earth, and that data, when it arrived, said something the models did not predict. The readings began to shift around 2020. Voyager 1's magnetometer, one of the 4 instruments still functioning on the spacecraft, recorded an abrupt increase in the intensity of the magnetic fields embedded in the thin interstellar plasma through which it was travelling. At roughly the same time, its plasma wave detector measured a corresponding rise in the density of charged particles around the spacecraft. These instruments are old. They were designed in the early 1970s. They have been operating continuously for nearly half a century in conditions of radiation, cold, and vacuum that would destroy most modern electronics. And yet they are precise. They are consistent. And what they were reported was not noise. Similar things had happened before. Several times since Voyager crossed into interstellar space in 2012, the instruments had registered temporary increases in magnetic field strength and plasma density. Scientists understood these as pressure waves. When the sun erupts, sending massive surges of plasma outward, those surges eventually crash against the boundary of the heliosphere, the edge of the sun's domain. That collision sends reverberations outward into interstellar space, compressing the surrounding plasma and briefly intensifying its magnetic field. The effect is like a piston, a pulse of pressure that travels outward, disturbs the medium for a while, and then fades as the energy dissipates. Every previous event had faded. The numbers rose, held for weeks or months, and returned to baseline. That was the pattern. That was the expectation. In 2020, the numbers rose again, and they did not come back down. Week after week, the readings remained elevated, month after month. The team waited for the familiar return to normal. It did not arrive. By the time a full year had passed with no sign of the anomaly abating, the conversation inside the mission team had shifted. This was no longer a transient event. Voyager had either encountered a pressure wave of unprecedented size and duration, or it had drifted into something else entirely. A region of space with fundamentally different properties. A structure. That word structure is used with great care in science. It implies boundaries. It implies organization. It implies that whatever Voyager had entered was not a random smear of slightly denser material, but something with a shape, with edges, with characteristics that distinguish it from the surrounding medium. Using that word means committing to the idea that the space between stars is not uniform, that it has geography, that there are places within it, distinct from other places, the way a warm current differs from the cold water around it, even though both are part of the same ocean. And then came the silence. In November 2023, Voyager 1 stopped making sense. Its transmissions continued to arrive on Earth, but the data inside them was garbled, unreadable, a stream of ones and zeros repeating in a pattern that carried no scientific information. The spacecraft was alive, but unable to speak coherently. Engineers traced the problem to a corrupted memory chip in the flight data subsystem, one of the 3 onboard computers. A single chip, likely damaged by a high-energy cosmic ray particle, or simply worn out after nearly 5 decades of continuous operation, had broken the link between the instruments and the transmitter. For 6 months, the team at the Jet's propulsion laboratory worked to fix it. The difficulty of the task is hard to overstate. Every command sent to Voyager takes more than 23 hours to arrive. Every response takes the same amount of time to return. A single exchange, 1 question and 1 answer, takes nearly 2 full days, and the computer they were debugging was built with technology that predates the personal computer. It has no operating system in the modern sense. It has no graphical interface. It is by current standards barely a computer at all, and it was 15 billion miles away. They rewrote the software. They found a way to route the data around the damaged memory block, distributing the code across other parts of the system. In April 2024, engineering data began flowing again. In May and June, science data from 2 and then all 4 remaining instruments resumed. Voyager was talking again. And the first thing scientists wanted to know was whether the anomaly was still there, whether the elevated magnetic field and plasma density readings that had persisted since 2020 were still present after 6 months of silence. The answer, as the data came in and was processed, appeared to be yes. Voyager 1, it seemed, was still inside whatever it had drifted into, still surrounded by a medium denser and more magnetically intense than the baseline of interstellar space, still by every measurement available within a structure that no model of the region had predicted. This is where the story begins, not with an answer, because there is no definitive answer yet, not with a revelation, because the data is still being analysed and debated. It begins with a question, the kind of question that has a way of expanding the longer you sit with it, a question that starts small and specific. What did Voyager detect, and grows until it touches something much larger? What is the space between the stars actually like? What have we been wrong about? And how much of the universe remains completely unknown to a species that has only ever sent 2 functioning instruments beyond the edge of its own star's influence? To follow that question properly, we need to go back, not to 2020, when the anomaly began, not to 2012, when Voyager crossed into interstellar space, back to the beginning, back to a September morning in 1977 when a rocket carrying a small machine and a golden record climbed into the Florida sky and began a journey that no one involved in its construction expected to last this long. Before we do, let this settle for a moment. There is a machine out there, right now, that was touched by human hands. Engineers tightened its bolts, technicians tested its circuits, someone soldered its wires and someone else checked the work. It was loaded onto a rocket by people who packed lunches and drove home on highways and had families waiting for them at the end of the day. Ordinary people built this extraordinary thing, and now it floats in a place so remote that if you could somehow stand beside it and look back toward home, you would not be able to find Earth. Not with your eyes, not with a telescope. The sun itself would be just another star, unremarkable among billions. A faint point of light in a sky so dense with stars that picking it out would be like identifying a single grain of sand on a beach from a mile away. That distance matters. It is not a number to skim past. 15 billion miles. Light, the fastest thing in the universe, takes more than 23 hours to cover that distance. A commercial airplane flying non-stop would take over 3 million years. The distance is so vast that it defeats every analogy built from the scale of a human life. Your mind cannot hold the words 15 billion miles. It cannot hold the distance itself. No mind can. All we can do is accept that the number is real, that the machine is there, and that the space it occupies is farther from warmth and light and life than anything we have ever created. And in that space, in that cold, in that silence, the instruments are still running. The magnetometer still measures. The plasma wave detector still listens. The cosmic ray telescope still counts the high energy particles that stream through the galaxy, remnants of stars that exploded before our sun was born. These instruments whisper their findings into a transmitter that broadcasts with the power of a refrigerator light bulb, and those whispers cross 15 billion miles of void and arrive at a radio dish in the Australian outback, where they are recorded and forwarded to a team of scientists who have spent their careers listening to the quietest voice in the solar system. That voice said something strange, and the people listening could not explain it. Not immediately, not fully, perhaps not ever, given how little time Voyager has left before its power finally fades and the voice goes silent for good. But for now, the voice continues, and the story it tells begins not in the dark between stars, but under a blue sky on a warm morning at the edge of an ocean, where a rocket waited on a launch pad with a golden record bolted to its side in a trajectory plotted toward forever. Take a breath. We have a long way to travel. The summer of 1977 was unremarkable by most measures. Star Wars had just opened in theatres. The New York City blackout had plunged millions into darkness for 25 hours. Elvis Presley would die in August, and the son of Sam would be arrested 6 days later. The world was busy with its own dramas, its own urgencies, its own small and large catastrophes. Almost nobody was paying attention to what was happening at Cape Canaveral. On August 20th, a Titan III-E rocket carrying a spacecraft called Voyager 2 lifted off and climbed into a clear Florida sky. 16 days later, on September 5th, a second rocket carrying Voyager 1 followed it into space. The naming is worth noting because it causes confusion even now. Voyager 2 launched first, Voyager 1 launched second, but Voyager 1 was placed on a faster trajectory, a more direct route through the outer solar system, and it overtook its twin within months. By December 1977, Voyager 1 was ahead, and it has been ahead ever since. The reason both spacecraft launched in the same narrow window was not impatience, it was geometry. The 4 giant planets of the outer solar system, Jupiter, Saturn, Uranus and Neptune, were approaching an alignment that happens once every about 176 years. In this configuration, a spacecraft could use the gravity of one planet to accelerate toward the next like a stone skipping across water, gaining speed with each bounce rather than losing it. Without that alignment, visiting all 4 planets in a single mission would have required far more fuel than any rocket of that era could carry. The window was open. It would not open again until the 22nd century. If they were going to do it, it had to be now. The spacecraft themselves were marvels of practical engineering rather than elegance. Each one weighed 815 kilograms at launch, roughly the weight of a large horse. They were assembled by hand at the Jet Propulsion Laboratory in Pasadena, California, in clean rooms where technicians wore white suits and gloves to avoid contaminating the sensitive instruments. The onboard computers had a total memory of about 69 kilobytes, less than a single photograph taken by a modern phone. The computers could execute about 81,000 instructions per second. For comparison, the device you might be listening to this on can execute billions. But those computers did not need to be fast. They needed to be reliable. They needed to survive radiation, temperature extremes, and decades of continuous operation in conditions that no engineer could fully predict. And they have. Nearly 50 years later, the computers are still running, slowly, patiently, executing instructions that were written by people who could not have imagined they would still be relevant in the 21st century. Power came from 3 radioisotope thermoelectric generators, cylinders packed with pellets of plutonium-238, a radioactive isotope that generates heat as it decays. That heat is converted into electricity through a process called the thermoelectric effect, the same principle that makes certain materials produce a voltage when one side is hotter than the other. At launch, the 3 generators together produced about 470 watts, enough to run a few household appliances. That number has been declining ever since, by roughly 4 watts per year, as the plutonium steadily decays and the thermocouples that convert heat to electricity slowly degrade. As of the most recent data, the generators produce less than half of their original output. The engineers have compensated by turning off every non-essential system. Heaters have been shut down. Backup instruments have been powered off. The spacecraft operates now at temperatures far below what it was designed for, and every remaining watt is rationed with the precision of a besieged city counting its last stores of food. But in 1977, power was abundant. The instruments were all functioning, and the solar system was waiting. Voyager 1 reached Jupiter in March of 1979 after a journey of about 18 months. What it found there was not what anyone had prepared for. The Great Red Spot, that iconic storm large enough to swallow Earth, was more complex and more violent than ground-based telescopes had suggested. But the real shock came from the moons. Europa, a world slightly smaller than Earth's moon, appeared to have a surface of smooth ice, cracked and ridged, with almost no craters. The absence of craters meant the surface was young, constantly renewed, which implied something was heating the interior. The most likely candidate was an ocean of liquid water beneath the ice, kept warm by tidal forces from Jupiter's immense gravity. And then there was Io, the innermost of Jupiter's large moons. Io was expected to be a dead, cratered world, frozen and inert. Instead, Voyager's cameras captured something that made scientists across the world lean forward in their chairs. Plumes. Enormous plumes of material erupting from the surface and arcing hundreds of kilometers into space. Io was volcanically active. Wildly active. The most volcanically active body in the entire solar system, it would turn out. No one had predicted this. No model had suggested it. A paper proposing tidal heating of Io had been published just days before the flyby, but it was considered speculative at best. Voyager turned speculation into confirmed, photographed, undeniable reality. It was the first time active volcanism had been observed anywhere other than Earth. Voyager also discovered that Jupiter had a thin, faint ring, not the grand rings of Saturn, but a delicate structure of dust and small particles orbiting close to the planet, invisible from Earth but clearly visible in the geometry of Voyager's approach. Two previously unknown moons, Thebe and Metis, were identified in the images as well. Each discovery was a gift, but each flyby was also a tool. Jupiter's gravity bent Voyager's trajectory and accelerated it, hurling it onward towards Saturn like a ball thrown from a spinning carousel. The spacecraft was going faster now than any propulsion system had made it go. It was borrowing speed from the planet itself, trading a negligible fraction of Jupiter's orbital momentum for a significant boost to its own velocity. This is the beauty of gravity assists. They cost nothing. They require no fuel. They simply require that you be in exactly the right place at exactly the right time, and that the planet you are passing be massive enough to bend your path and throw you forward. Saturn was waiting. Voyager 1 arrived in November 1980. The rings, seen up close for the first time, were not the smooth bands they appeared to be from Earth. They were composed of thousands of individual ringlets, separated by gaps of varying width, structured by the gravitational influence of small moons embedded within them like shepherds tending a flock. Voyager discovered 5 new moons at Saturn and a previously unknown ring, designated the G-ring. But the most consequential encounter was not with Saturn itself. It was with Titan, Saturn's largest moon. Titan was known to have an atmosphere, one of the few moons in the solar system to possess one. The atmosphere was thick and opaque, a dense orange haze of nitrogen and organic compounds that hid the surface completely. Scientists wanted to see what was beneath that haze. They wanted to understand what kind of world could hold an atmosphere denser than Earth's at a distance from the Sun, where temperatures hover near minus 180 degrees Celsius. Voyager 1's flyby of Titan was designed to pass as close as possible to the Moon, sweeping through its upper atmosphere to gather data on its composition, temperature, and pressure. The encounter was a success. Voyager confirmed that Titan's atmosphere is primarily nitrogen, just like Earth's, with a surface pressure about 1.5 times that of our own planet. Methane and other hydrocarbons were detected, suggesting a world where methane might play the role that water plays on Earth. forming clouds, falling as rain, pooling in lakes. But this encounter came at a cost. The trajectory required to fly close to Titan sent Voyager 1 on a path that curved sharply upward, out of the plane of the solar system. There would be no Uranus flyby, no Neptune. The choice had been made deliberately. Titan, with its atmosphere and its potential for complex chemistry, was judged more scientifically valuable than a distant flyby of Pluto, which was the other option the trajectory could have accommodated. The mission planners chose the Moon with the atmosphere over the small, distant world at the edge of the known solar system. It was the right choice, by most accounts, but it meant Voyager 1 was done with planets. From Saturn onward, there would be no more grand encounters, no more close-up photographs of swirling clouds and icy moons. The spacecraft was heading out and further out, climbing away from the plane where the planet's orbit aimed at a direction that would eventually carry it beyond the reach of the sun itself. The planetary mission was over. What came next was something no one had originally planned for, something that would take 32 more years to reach its most important moment, and something that began not with a destination, but with a decision to keep listening. But before we follow Voyager into the dark, there is one more detail from its construction that deserves attention. Bolted to the side of each Voyager spacecraft is a 12-inch golden phonograph record, sealed in an aluminium cover and accompanied by a cartridge and stylus for playback. The cover is electroplated with uranium-238, an isotope whose decay rate provides a clock that any sufficiently advanced civilization could use to determine how long ago the record was made. The contents of the golden record were selected by a committee chaired by astronomer Carl Sagan. The task was, in Sagan's words, to create a portrait of our planet and our species that could speak across the unimaginable distances of interstellar space to a mind that might be wholly unlike our own. The record contains greetings in 55 human languages, from ancient Sumerian to modern English. It contains 35 sounds from life on Earth, including the calls of humpback whales, the chirping of crickets, the roar of a rocket launch, and the laughter of a child. It contains 90 minutes of music, ranging from Bach to Beethoven to Chuck Berry to traditional songs from Peru, Japan and Senegal. It contains 115 images encoded as audio signals, including photographs of a woman nursing an infant, a man eating a piece of fruit, the structure of DNA, and the mathematical equations that describe the forces governing the universe. It is, in a sense, the most ambitious letter ever written, addressed to no one in particular, sent with no expectation of a reply, carried by a machine that will drift through the galaxy for hundreds of millions of years after its power has failed and its instruments have gone silent, and the civilization that built it has either flourished beyond recognition or vanished entirely. Sagan knew the record was unlikely to be found. He said so publicly. The probability of another intelligence intercepting a single object in the vastness of interstellar space is effectively zero over any timescale a human mind can grasp. But Sagan argued that the record was not really for them, whoever they might be. It was for us. It was an act of self-definition, a statement about what kind of species we are, or at least what kind of species we aspire to be. A species that sends music into the dark, that includes whale songs alongside equations, that tells the universe, here is what we sound like, here is what we care about, here is what we are. The record is still out there, still bolted to the side of the spacecraft, still carrying the sound of rain and the greeting of a child, still heading outward into the space between the stars, into whatever structure or void or field of ancient plasma lies ahead. The cameras were still on when Voyager left Saturn. They would remain on for another 10 years, pointing occasionally at targets of opportunity, recording the shrinking shapes of the outer planets as they receded into the distance. But the real work of observation was shifting. Voyager was no longer a planet hunter. It was becoming something new, something for which there was no precedent and no playbook. It was becoming an interstellar probe, and the first thing it would need to do before it could study the space between the stars was look back one last time at the place it came from. On February 14th, 1990, Voyager 1 was approximately 6 billion kilometers from Earth. It had been travelling for 12.5 years. The planetary encounters were a decade behind it. Ahead lay nothing but open space, a gradually thinning solar wind, and the slow climb toward the boundary of the sun's influence. The spacecraft's cameras, which had produced some of the most stunning images in the history of exploration, were no longer needed for the mission. There was nothing ahead to photograph. The instruments that mattered now were the ones that measured particles and fields, invisible things, the stuff you detect with magnetometers and plasma sensors, not lenses. Carl Sagan had an idea. He had been pushing for it for years, quietly, persistently, with the kind of gentle stubbornness that characterized much of his work. He wanted Voyager to turn its camera around, not to look at anything in particular, not to photograph a planet or a moon or a ring system. He wanted Voyager to look back at Earth, one last time, from the greatest distance any camera had ever been from home. He wanted to see what our planet looked like from the edge of the solar system. There were objections. The camera was old. Turning the spacecraft to aim it toward the inner solar system would point its optics dangerously close to the sun, risking permanent damage to the imaging system. And what would the photograph show? At 6 billion kilometers, Earth would be smaller than a single pixel, a dot, barely distinguishable from the scattered light in the camera's optics. What scientific value could such an image possibly have? Sagan argued that the value was not scientific, it was something else, something harder to quantify but no less real. He believed that seeing our planet from that distance, seeing it as it truly is in the context of the cosmos, would matter, not to the instruments, to us. NASA agreed. On February 14th, Voyager 1 turned its camera toward home and took a series of photographs that would later be assembled into a mosaic called the Family Portrait, a wide view of the solar system from outside. Within that mosaic, in a single frame, was Earth, a pale blue dot, suspended in a beam of sunlight scattered through the camera's optics. The dot occupied less than a single pixel. It was almost invisible. You had to know where to look to find it. Sagan wrote about that image with a clarity and tenderness that has outlasted almost everything else he produced. He described the dot as the entirety of human history. Every king and peasant, every saint and sinner, every young couple in love, every mother and father, every inventor and explorer, every teacher of morals, every corrupt politician, every creator and destroyer of civilization, every moment of hope and every moment of despair, all of it taking place on a mote of dust suspended in a sunbeam. He urged humility. He urged kindness. He urged the recognition that in the face of the vastness that Voyager had revealed, our petty differences and our inflated sense of importance were, at best, a misunderstanding of our actual position in the cosmos. The photograph is now one of the most reproduced images in history. It hangs in classrooms and observatories and living rooms around the world. It has been referenced in speeches and eulogies and wedding vows. It has become, in a way that Sagan might have predicted but could not have guaranteed, a kind of mirror, a way of seeing ourselves not as we imagine we are, but as we actually are, small, fragile, alone on a tiny world in a vast and mostly empty universe, and yet somehow capable of building the thing that took the photograph, capable of sending it 6 billion kilometers into space, capable of turning it around and looking back. There is a particular quality to the pale blue dot that separates it from every other photograph of Earth ever taken. The Apollo photographs, beautiful as they are, show a planet that is recognizable. You can see continents, you can see clouds, you can identify with a little effort where you live. The image carries the comforting implication that Earth is large and significant, a bright marble against the black. The pale blue dot carries no such comfort. The Earth in that photograph is not a marble. It is barely visible. It is a mote caught in a sunbeam, and the overwhelming impression is not of significance, but of smallness, of vulnerability, of the terrifying, beautiful improbability of the fact that everything you have ever known or loved exists on that imperceptible speck and nowhere else. There is a loneliness in that image that is difficult to articulate, not the loneliness of an individual, but the loneliness of a species. Everything we have ever known, every face we have ever loved, every piece of music we have ever heard, every meal shared and conversation held and dream imagined, all of it happened on that dot. There is no backup. There is no second location. If you zoom out far enough, as Voyager did, all of human experience collapses into a single point of light that could be blotted out by a grain of sand held at arm's length. The universe does not need us. It does not notice us. And yet we noticed it. We built a machine to go and look, and then we had the courage, or perhaps the recklessness, to turn that machine around and look at ourselves. After the family portrait was taken, the cameras were shut down. There was no reason to keep them running. They consume power that the spacecraft would need for the decades of operation ahead, and there was nothing left for them to see. Voyager 1 would never take another photograph. From that moment forward, it would experience the universe only through its remaining instruments, measuring things that have no visual form: magnetic fields, plasma densities, the energy of cosmic ray particles, the oscillation of electrons in interstellar gas, a universe of numbers rather than images, a universe you hear rather than see. This transition matters more than it might seem. When Voyager was a planet explorer, the public could engage with it through photographs. You could see Jupiter's clouds, you could see Io's volcanoes. You could look at Saturn's rings and feel, viscerally, the strangeness and beauty of the outer solar system. Those images connected people to the mission in a way that was immediate and emotional and required no scientific training to appreciate. After the cameras were turned off, that connection became harder to maintain. Voyager's discoveries from that point forward would be expressed in graphs and data tables and papers published in journals that most people would never read. The beauty of what it found would be invisible to the eye, detectable only through instruments and interpretable only through mathematics. This is not a failure of the mission. It is the nature of the frontier it was entering. The space between stars does not photograph well. It is not colourful or dramatic or visually striking. It is dark and cold and mostly empty, and the things that make it interesting are woven into the fabric of its invisible fields and particles. But those invisible things, it would turn out, are where the most profound discoveries were waiting. The cameras showed us what the planets look like. The instruments that remained would show us what the universe is made of. And the universe, it would turn out, is made of things we did not expect, arranged in ways we did not predict, behaving according to rules we do not yet fully understand. For the next 14 years after the cameras went dark, Voyager 1 travelled in relative quiet. It crossed the orbits of the outermost known planets. It passed through regions of space that had never been directly sampled by any instrument. The solar wind continued to flow past it, a thin stream of charged particles blown outward from the sun at roughly 400 kilometers per second. carrying with it the sun's magnetic field, stretched and twisted by the rotation of the star like thread pulled from a spinning wheel. As Voyager moved farther from the sun, the solar wind grew thinner, the magnetic field grew weaker, the particles became more sparse. The spacecraft was approaching the edge of the sun's domain, the place where the outward pressure of the solar wind is finally balanced by the inward pressure of the interstellar medium, the material that fills the space between the stars. That boundary was not a wall, it was not a sharp line drawn across the sky. It was a gradual transition, a region where two environments meet and mix and push against each other like two weather fronts converging over a plain. Scientists had theories about what this boundary would look like. They had models and predictions and decades of indirect observation to guide their expectations. The boundary should have certain properties. The magnetic field should change direction. The particle density should jump. The temperature should shift. The character of the cosmic rays should transform from solar-dominated to galactic-dominated. These predictions were reasonable. They were grounded in solid physics, and as Voyager 1 approached the boundary, it began to test them one by one. Some of the predictions turned out to be correct. Many did not. What Voyager found at the edge of the solar system was stranger, more complex, more layered, and more dynamic than any model had suggested. The neat, clean boundary that textbooks described was, in reality, a churning, foamy, magnetically tangled zone that defied easy characterization and forced scientists to revise their understanding of the environment we live in. The journey to that boundary, from the cameras going dark in 1990 to the first signs of the edge in 2004, took 14 years of steady, quiet travel. 14 years of dwindling power and degrading instruments and shrinking budgets and the slow, unglamorous work of keeping a 50-year-old machine alive in the cold. 14 years during which the public largely forgot about Voyager, distracted by newer missions and closer targets and the constant churn of the news cycle. But the scientists never forgot. They were waiting, listening, counting every particle and measuring every field, because they knew that ahead of Voyager, closer with every passing hour, was a frontier that no human instrument had ever reached, a place where the sun's influence ends and the true nature of interstellar space begins. The first sign came in December 2004, and it was not subtle. But the years between the photograph and that first sign deserve more than a passing mention, because those years, the quiet ones, the ones that did not make headlines, were the years that made everything that followed possible. They were the years of maintenance, of vigilance, of a small team of engineers at the Jet Propulsion Laboratory who came to work every day and checked the telemetry, and adjusted the power budget, and nursed a spacecraft through the slow degradation of age, not because anyone was watching, but because the machine was still working and the frontier was still ahead. There is something deeply human about that kind of persistence, about caring for something that most of the world has forgotten, about believing that the quiet accumulation of data, day after day, year after year, will eventually amount to something that matters. The Voyager team during those years was small. Budgets were tight. The glamorous years of planetary encounters were long past, and the interstellar mission, officially designated the Voyager Interstellar Mission, or VIM, operated with a fraction of the resources it had once commanded. And yet the work continued. The antennas kept listening. The instruments kept measuring. And Voyager kept moving outward, 3 astronomical units per year, roughly the distance from Earth to the Sun every 4 months, heading for a boundary that no one knew the exact location of. The predictions varied. Some models placed the termination shock, the first major boundary of the heliosphere, at 75 astronomical units from the Sun. Others placed it at 90 or beyond. The uncertainty reflected how little we actually knew about the shape and extent of our own star's influence. We could model it. We could theorize. But until something crossed it and reported back, the models remained untested. Voyager 1 would be the test. And the results, when they came, would begin a pattern that has repeated at every boundary the spacecraft has crossed since. The pattern is this. Nature is more complicated than the model, every time, without exception. What scientists expected to find was simpler than what Voyager actually found. And every revision, every surprise, every moment of confusion followed by slow understanding, has made our picture of the universe a little more honest and a great deal more strange. The termination shock was waiting. 94 astronomical units from the Sun, roughly 8.5 billion miles, a distance that light covers in about 13 hours, a distance that Voyager, at its speed, had taken 27 years to reach. What happened when it arrived that changed everything scientists thought they knew about the edge of the solar system? Imagine you are standing in a field on a windy day. The wind is blowing steadily from the west, bending the grass, pushing at your clothes, filling the air with motion. Now imagine walking east, into the wind, for a very long time. At first the wind is strong and constant, but as you walk, you notice it weakening, not disappearing, not stopping, but losing its force. The gusts that once pushed you backward now barely register. The grass stands taller, the air grows quieter, and then, at some point that is hard to pinpoint exactly, you realise the wind is no longer coming from behind you. Something else is pushing back, a different pressure from the east, faint but present, and the two pressures are meeting somewhere near where you stand, cancelling each other out, creating a zone of turbulence and confusion where neither force fully dominates. That is, in the broadest possible terms, what happens at the edge of the solar system. The wind in this analogy is the solar wind, a continuous stream of charged particles that the sun blows outward in every direction at speeds of roughly 400 kilometers per second. This wind carries the sun's magnetic field with it, stretching it outward like taffy pulled from a spinning stick, filling a vast volume of space with the sun's influence. That volume is the heliosphere. And Voyager 1, after 27 years of continuous travel, was about to reach its first boundary. The termination shock is the point where the solar wind, which has been racing outward at supersonic speeds, abruptly slows down. It doesn't stop, it slows. The reason is the interstellar medium, the thin material that fills the space between stars, which exerts its own pressure inward against the solar wind. At some distance from the sun, those two pressures reach a rough equilibrium, and the solar wind can no longer maintain its supersonic pace. It crashes in a sense, like a wave hitting a seawall. The energy doesn't vanish. It converts from the kinetic energy of fast-moving particles into heat and magnetic compression. The region gets warmer. The magnetic field gets stronger. The character of the particle environment changes abruptly. On December 16th, 2004, at a distance of approximately 94 astronomical units from the Sun, which is about 8.5 billion miles, Voyager 1 crossed the termination shock. An astronomical unit is the distance from the Earth to the Sun, roughly 93 million miles. Voyager was now 94 times that distance from the star that had birthed it, out past all the planets, past the Kuiper Belt, past the orbits of every known body in the solar system, and it was just now reaching the first boundary of the Sun's influence. The scale of the heliosphere is difficult to hold in a human mind. It took Voyager 27 years, travelling at 38,000 miles per hour, to reach a boundary that is still well within the Sun's overall domain. The edge of the heliosphere is not the edge of the solar system, it is merely the edge of the Sun's wind. What Voyager found at the termination shock matched some predictions and defied others. The solar wind did slow down. The magnetic field did intensify. The particle environment did change. But the shock itself was not the clean, well-defined boundary that models had drawn. It was messy. It was dynamic. It appeared to move, breathing in and out as the sun's activity waxed and waned over its 11-year cycle. Voyager might have crossed the termination shock more than once, passing through it as it rippled back and forth across the spacecraft's position. The neat line on the diagram was, in reality, a churning, shifting, unstable zone that refused to sit still. Beyond the termination shock lay the heliosheath. If the termination shock is where the solar wind slows down, the heliosheath is where the slowed wind piles up. Picture a river flowing into a lake. At the river's mouth, the fast-moving water suddenly encounters the slow-moving water of the lake. It doesn't just stop. It spreads out. It swirls. It creates eddies and pockets of turbulence where the two waters mix. The heliosheath is that mixing zone. The solar wind, now slowed to subsonic speeds, fills this region with a thick, warm, magnetically tangled medium that is neither purely solar nor purely interstellar. Voyager spent 8 years in the heliosheath, from 2004 to 2012, and during those 8 years it made discoveries that no model had anticipated. The first surprise was the magnetic bubbles. Scientists had expected the sun's magnetic field in the heliosheath to be smooth and stretched, pulled into long, curving lines by the solar wind's outward flow. Instead, Voyager found that the magnetic field was broken up into a froth of individual bubbles, each one roughly 100 million miles across. These bubbles were created by the twisting and folding of the sun's magnetic field lines, which at that distance had become so contorted by the sun's rotation that they snapped and reconnected, forming discrete pockets of magnetic energy rather than continuous sheets. The heliosheath was not a smooth boundary layer. It was foamy, turbulent, complex in ways that required entirely new models to describe. The second surprise was the particle behavior. Anomalous cosmic rays, particles that are accelerated to high energies at the termination shock, were expected to peak in intensity right at the shock and then decline as Voyager moved deeper into the heliosheath. Instead, the intensity of these particles continued to rise well beyond the termination shock, reaching levels that the models could not account for. Something was accelerating particles more efficiently than anyone had predicted, and the acceleration was not confined to the shock boundary itself. The third surprise, and perhaps the most unsettling, was the density. Instead of a gradual transition from the thin solar wind to the denser interstellar medium, Voyager recorded sudden spikes and drops in particle concentration. The heliosheath was not uniform. It had pockets of higher and lower density, regions where particles were compressed and regions where they were sparse, arranged in a pattern that suggested the heliosheath was being actively shaped by forces that the spacecraft could detect but not fully characterize. This was not the edge scientists had imagined. The textbook picture of the heliosphere, a smooth bubble with a clean outer boundary, was being replaced by something far more complicated. The edge of the sun's domain was not a wall. It was a weather system, dynamic, variable, full of structures and surprises, driven by the interaction of two cosmic forces, the solar wind from inside and the interstellar medium from outside, that were locked in a continuous shifting negotiation. There is something worth pausing on here, something about the nature of boundaries that applies to the heliosheath, and as we will see, to everything Voyager would encounter afterward. We tend to think of boundaries as lines. A fence separates your yard from your neighbour's. A coastline separates land from sea. A border on a map separates one country from the next. These are clean, human-scale boundaries that our minds handle easily. But nature does not draw lines. Nature draws gradients. The shore is not a line between land and ocean. It is a zone of tide pools and wet sand and crashing waves where the two environments overlap and merge, and neither one fully dominates. The edge of a forest is not a line between trees and open field. It is a band of thinning canopy and increasing light where both environments coexist. The heliosheath is that kind of boundary. It is not the place where the solar system ends and interstellar space begins. It is the place where the two environments overlap, where solar material and interstellar material mix and push against each other and create something that is neither purely one nor purely the other. Understanding this is important for understanding everything that follows, because the structure that Voyager would eventually detect exists in a universe where boundaries are not walls but zones, where transitions are not sudden but gradual, and where the space between things is often more interesting than the things themselves. Scientists were also grappling with a more fundamental question during Voyager's transit through the heliosheath. What shape is the heliosphere? For decades, the standard picture showed a comet-like form, with a blunt nose facing the direction of the sun's motion through the galaxy and a long tail streaming behind, stretched by the interstellar wind like the tail of a kite. This made intuitive sense. The sun is moving through the interstellar medium at roughly 23 kilometers per second. The solar wind should be compressed at the front and stretched at the back, creating an asymmetric shape. But data from the Cassini spacecraft, which was orbiting Saturn and detecting energetic neutral atoms from the heliosphere's boundary, suggested something different. The energetic neutral atom signatures appeared roughly equal from all directions, which some researchers interpreted as evidence for a more spherical shape. The heliosphere, they argued, might be closer to a bubble than a comet. Nathan Schwadron at the University of New Hampshire pushed back forcefully, arguing that the Cassini data had been misinterpreted and that the apparent symmetry simply reflected changes in the solar cycle rather than the actual shape of the heliosphere. The debate was intense, and as of Voyager's transit through the heliosheath, unresolved. Two data points cannot define a three-dimensional shape. Voyager 1 and Voyager 2 crossed the heliosphere at different locations and different times, heading in different directions. They were like two explorers crossing the Sahara on different paths and trying to determine the shape of the entire desert from what they saw along the way. Insufficient, suggestive, tantalizing, but not conclusive. The shape of the bubble we live inside remains, even now, one of the open questions in heliophysics. We know the heliosphere exists. We know approximately how large it is. We do not know with certainty what it looks like from outside. And all of this was just the heliosheath. The actual boundary, the heliopause, where the sun's influence truly ends and interstellar space truly begins, was still ahead. Voyager was getting closer. Year by year the signs accumulated. Galactic cosmic rays, high-energy particles that originate from distant exploding stars, began to increase in number. These particles are normally blocked or deflected by the heliosphere. Their increasing presence meant the heliosphere's shielding was thinning. Voyager was nearing the outer wall. In December 2011, NASA announced that Voyager 1 had entered what they called a cosmic purgatory, a stagnation region where the solar wind had slowed to zero, and the sun's magnetic field had doubled in intensity, as if compressed by the pressure of interstellar space pressing inward. Charged particles from inside the heliosphere were slowing and turning back. Particles from outside were pouring in at rates 100 times higher than before. The spacecraft was balanced on the edge of two environments, not quite in one and not quite in the other, a threshold that seemed to shimmer and shift every time instruments tried to pin it down. Ed Stone, the Voyager project scientist at Caltech, described it with characteristic understatement. Voyager had discovered a new region of the heliosphere that they had not realized was there. They were still inside, apparently, but the magnetic field was now connected to the outside. It was like a highway, Stone said, letting particles in and out. The metaphor was apt. The boundary was not a closed door. It was a membrane, permeable, selective, dynamic. The kind of boundary that lets some things through and blocks others, and changes its mind about which is which, depending on conditions that shift from week to week. The team waited. The data continued to stream in, 23 hours per transmission, each reading a snapshot of an environment in flux. The magnetic field was behaving strangely. The particle counts were swinging between solar and galactic dominance. Something was about to happen. Everyone could see it in the data. The crossing was close. It came in the summer of 2012, and when it did, it was both everything scientists had hoped for and almost nothing they had predicted. August 25th, 2012, a Sunday. On Earth, the Summer Olympics were winding down in London. Neil Armstrong, the first human to walk on the moon, died that day at the age of 82. The news was dominated by a tropical storm approaching the Gulf Coast. Nobody outside a small community of space scientists knew that roughly 11 billion miles away, a machine built 35 years earlier was about to do something that no human creation had ever done. It crossed the heliopause, the final boundary of the sun's domain. The place where the outward pressure of the solar wind, the stream of charged particles that the sun has been exhaling since it ignited 4.5 billion years ago, is finally overwhelmed by the inward pressure of the interstellar medium. Beyond this line, the sun no longer rules. The material surrounding the spacecraft is no longer of solar origin. It is interstellar. It was forged in the furnaces of other stars, expelled into the galaxy by stellar winds and supernova explosions, drifting through the void for millions of years before Voyager arrived to sample it. But the crossing was not clean. It was not a moment of sudden clarity. It was, like almost everything Voyager had encountered at the edge, ambiguous and confusing and deeply resistant to simple characterization. The problem was the magnetic field. Every model of the heliopause predicted that when Voyager crossed from the heliosphere into interstellar space, the direction of the magnetic field should change. Inside the heliosphere, the magnetic field is shaped by the sun. It has a specific orientation determined by the sun's rotation and the geometry of its magnetic poles. Outside the heliosphere, the magnetic field should be shaped by the galaxy, by distant stars and ancient processes that have nothing to do with our sun. The two fields should point in different directions. Crossing from one to the other should produce a measurable, unambiguous change in the magnetic field's orientation. That change did not happen. The magnetic field intensity increased as expected. The particle environment changed dramatically. Cosmic rays from outside the solar system surged, solar wind particles vanished. By every particle-based measure, Voyager had left the heliosphere, but the magnetic field continued to point in roughly the same direction it had pointed inside the heliosphere, as if the boundary, clear in every other respect, and had somehow failed to rotate the magnetic field. This was deeply confusing. Stamarios Krimigis, a principal investigator on one of Voyager's particle instruments, later described it with a kind of bemused frustration. Nature, he said, hadn't read the theorist's papers and didn't know it was supposed to change the magnetic field direction. The comment captured something important about the relationship between models and reality. Models are our best guesses. Reality is under no obligation to match them. The confusion meant that for more than a year after the crossing, scientists could not definitively confirm that Voyager had entered interstellar space. The particle delta said yes. The magnetic field delta said maybe not. The The spacecraft's plasma science instrument, which could have settled the question by directly measuring the density of the surrounding plasma, had stopped working in 1980. Without that instrument, the team had no direct way to measure the 40-fold increase in plasma density that should accompany the transition to interstellar space. They needed another method. The sun, of all things, provided one. Solar storms that erupted in March 2012 sent waves of energy outward through the solar system. Those waves travelled slowly compared to light, taking more than a year to reach Voyager's position. When they arrived, they shocked the plasma surrounding the spacecraft, causing electrons in that plasma to oscillate. Those oscillations produced radio waves that Voyager's plasma wave subsystem could detect. The frequency of the oscillations depends directly on the density of the surrounding plasma. Higher density produces higher frequency. The frequency Voyager measured indicated a plasma density roughly 40 times higher than what it had measured inside the heliosphere. This was the smoking gun. The plasma density had jumped by the predicted factor. Voyager was in interstellar space. The official announcement came on September 12th, 2013, more than a year after the actual crossing. The generally accepted date of arrival is August 25th, 2012, the day the particle instruments first registered the durable change. There is something worth sitting with here. The first human-made object to reach interstellar space did so on a Sunday in August, and nobody knew it had happened. Not the scientists, not the public, not even the spacecraft, which has no awareness and simply continued executing its instructions, measuring its fields and particles, transmitting its data at the speed of light toward a planet it would never return to. The most significant boundary crossing in the history of human exploration went unrecognized for over a year. It was confirmed not by a dramatic event, but by the slow, patient work of scientists analysing numbers on screens in offices in Pasadena and Greenbelt and Cambridge. There was no champagne moment. There was a gradual accumulation of evidence that eventually reached a tipping point where denial was no longer scientifically defensible. This is how real discovery usually works, not with a shout, with a nod. And then there was the heat. Both Voyager 1 and later Voyager 2, which crossed the heliopause in November 2018, detected something unexpected at the boundary itself. The plasma just beyond the heliopause was hot. Not warm, hot. Temperatures in the range of 30,000 to 50,000 Kelvin, which is roughly 5 to 9 times hotter than the surface of the Sun. The local interstellar medium the space Voyager was heading into was known to have a temperature of only about 7,500 Kelvin. So why was the plasma at the boundary so much hotter? The answer, or at least the leading explanation, is compression. The interstellar medium is not stationary, it flows, and where it meets the heliosphere, it is compressed, squeezed by the pressure of the solar wind pushing outward. That compression heats the plasma, the same way pumping a bicycle tyre heats the air inside. The energy doesn't come from a fire or a chemical reaction, it comes from pressure. Particles are squeezed into a smaller volume, they move faster, and faster moving particles mean higher temperature. But the numbers were surprising. The degree of heating was greater than models had predicted. The boundary was energetically more extreme than anyone had expected. Some popular accounts described it as a wall of fire, which is dramatic but misleading. The plasma is incredibly thin, so thin that you could pass through it without feeling any warmth at all. Temperature, in physics, is a measure of how fast individual particles are moving. In a near vacuum, those particles are moving very fast, but there are so few of them that the total amount of thermal energy is negligible. You could stand in 50,000 Kelvin plasma of this density and feel nothing, but the measurement is real. The particles are genuinely moving that fast. And the reason they are moving that fast, at a boundary billions of miles from the nearest star, speaks to the extraordinary violence of the interaction between the heliosphere and the interstellar medium. Voyager 2's crossing, 6 years later, confirmed what Voyager 1 had found and added new details. Its plasma science instrument was still working, providing direct measurements that Voyager 1 could not make. It confirmed the density jump, it confirmed the temperature spike, and it added one more surprise. The magnetic field once again did not change direction at the heliopause. Whatever was causing this alignment between the solar magnetic field and the interstellar magnetic field was not a fluke. It was a real, persistent, unexplained feature of the boundary. Voyager 2 also found that the heliopause was not equally sealed in all directions. It crossed at a different location than Voyager 1, closer to the flank of the heliosphere rather than the nose. And at that location the boundary appeared to be more porous. Particles were leaking through both from inside out and from outside in quantities that suggested the heliosphere's protective function is not uniform. Some parts of the bubble are tighter than others. Some parts let more galactic radiation through. This has implications for Earth, though not immediate ones. The heliosphere shields our planet from more than 70% of galactic cosmic radiation, the high-energy particles produced by supernovae and other violent events across the galaxy. If the heliosphere's shielding varies with position and time, if solar activity and interstellar conditions can make it more or less porous, then the amount of cosmic radiation reaching Earth is not constant. It fluctuates over millions of years. Those fluctuations may have measurable effects on the planet's atmosphere, its climate, and perhaps even its biology. Some researchers have suggested that changes in the heliosphere's size and permeability, driven by the solar system's passage through regions of denser or thinner interstellar medium, may have influenced ice ages and evolutionary pressures on Earth over geological timescales. The evidence for these connections is indirect and debated, but the basic physics is sound. What happens at the edge of the heliosphere does not stay at the edge. It propagates inward, reaching every planet, every moon, every living thing that depends on the sun's protection. Voyager had crossed the boundary. It was in interstellar space. For the first time in history, a human instrument was directly sampling the medium between the stars, and the medium, it turned out, was not silent. It is worth understanding what interstellar space actually is, because the name itself is misleading. Interstellar space sounds like emptiness. It sounds like the absence of things, the space between defined by what it lacks, rather than what it contains. But interstellar space is not empty. It is full of material, spread so thin that by any human standard it would register as a perfect vacuum, but present nonetheless. Every cubic centimetre of the interstellar medium near our Sun contains roughly 1/10 of a particle. That is staggeringly empty by terrestrial standards. The air you are breathing right now contains about 25 billion particles per cubic centimetre. The interstellar medium is roughly 100 quintillion times less dense than the air in your lungs. But over vast distances, even that thin material adds up. The interstellar medium contains roughly 15% of the mass of our galaxy. It is the raw material from which new stars and planets will eventually form. It is the recycled remnant of stars that have already lived and died, their heavy elements scattered into the void by supernovae, mixed with primordial hydrogen and helium left over from the Big Bang. When Voyager measures the particles around it, it is touching the ashes of dead stars and the ingredients of stars not yet born. This medium is not uniform. It has regions of higher and lower density, hotter and cooler temperature, stronger and weaker magnetic fields. It has structure. It It has flows and currents and turbulence driven by the ongoing activity of the galaxy around it, supernova explosions, stellar winds, the gravitational influence of spiral arms and molecular clouds. It is an environment. A thin, cold, mostly dark environment, but an environment nonetheless with weather of its own. And Voyager, for the first time in human history, was reporting on that weather. Its instruments, designed decades ago for a completely different purpose, were functioning as the first interstellar weather station. Every measurement was unprecedented. Every reading was a first. There was no baseline to compare against, no previous mission to reference, no established normal. Voyager was writing the first page of a book that had never existed before. The question that drove the mission team from this point forward was straightforward in its phrasing and enormously difficult in its execution. What is out there? What is the interstellar medium actually like? And as the years passed and the data accumulated, the answer began to take a shape that no one had anticipated. A shape that suggested the space between the stars was more complex, more structured, and more surprising than any model had described. 3 months after crossing the heliopause in November 2012, Voyager 1 heard something. Not a signal in the way we typically use that word, not a transmission, not a message. It heard a vibration in the plasma surrounding it, a faint oscillation of electrons, set ringing by a disturbance that had originated at the Sun and travelled outward for more than a year before reaching the spacecraft's position. The oscillation was at a specific frequency, and that frequency told scientists something they had been waiting to learn. The density of the plasma was roughly 80 times higher than what Voyager had measured inside the heliosphere. This was the interstellar medium, sampled directly for the first time. The instrument that heard this was the plasma wave subsystem. It consists of 2 long antennas, each about 10 meters in length, extending from the spacecraft like the ears of a rabbit. These antennas are sensitive to electric field oscillations in the plasma, vibrations that occur when electrons are displaced from their equilibrium positions and oscillate back and forth at a frequency determined by how tightly packed they are. The more electrons per cubic centimetre, the higher the frequency. The fewer electrons, the lower. It is, in effect, a tuning fork for the density of space. In the heliosphere, this instrument had listened to the electrical activity of the solar wind, whistles and chirps and bursts of static, produced by the sun's constant exhalation of charged particles. Those sounds were familiar. Scientists had decades of data from the inner heliosphere to compare them against. But beyond the heliopause, the sounds changed. The familiar signatures of the solar wind faded. In their place came something new. At first the new sounds were intermittent. They appeared as discrete events, bursts of oscillation triggered by specific disturbances. Solar tsunamis, massive pressure waves launched by coronal mass ejections on the Sun, would travel outward through the solar system, cross the heliopause and slam into the interstellar plasma. Each impact set the plasma ringing, producing a brief, intense signal that Voyager could detect. These events were valuable. Each one provided a snapshot of the plasma density at that moment, a data point that scientists could use to track how the density of the interstellar medium changed as Voyager moved deeper into it. But between the tsunamis, the instruments picked up something else, a faint persistent signal, not a burst, not an event, a continuous emission barely above the noise floor of the instrument, present day after day, week after week. Stella Ocker, then a doctoral student at Cornell and now a postdoctoral fellow at Caltech, was the one who identified it. She developed techniques to filter the data and extract this weak signal from the background noise, and what she found was remarkable. The signal was a continuous plasma wave emission, a hum, a low steady vibration produced by the electrons in the interstellar medium, oscillating at a frequency that corresponded to the ambient density of the plasma through which Voyager was travelling. It was not produced by any specific event. It was the background noise of interstellar space itself, the electrical signature of the galaxy's thin, cold ancient medium, vibrating at a frequency set by its own properties. This is worth pausing on. Voyager was hearing the sound of the galaxy. Not metaphorically, not poetically, literally. The electrons in the interstellar medium, displaced by tiny fluctuations in pressure and density, were oscillating at a frequency that Voyager's antennas could detect and transmit back to Earth. The sound was quiet, fainter than the bursts produced by solar tsunamis, but it was there, persistent, continuous, the ambient hum of the space between the stars. If you could convert this signal to audio frequencies, scaling it up from the radio frequencies at which it actually occurs, it would sound like a low, steady drone, not musical, not melodic, but constant. A tone that has been playing since before the solar system existed, produced by material that has drifted through the galaxy for millions of years, carrying the magnetic fingerprint of whatever star or stellar nursery created it. The hum told scientists something they had suspected, but could not prove before Voyager began its interstellar journey. The interstellar medium is not static. It does not sit motionless between the stars like water in a still pool. It moves, it fluctuates. Its density varies from place to place and time to time, driven by forces that include the pressure waves from our own sun, the magnetic fields of the galaxy, and the ancient shock waves from supernovae that exploded millions of years ago. The hum is the indicator of that variation. As the plasma density around Voyager changes, the pitch of the hum changes with it. Higher density, higher pitch, lower density, lower pitch. Ocker and her colleagues described the significance in measured terms. For the first time, they were able to regularly sample the density of interstellar space over a very long stretch of distance, the longest ever measured. Previous density measurements had come only from the intermittent tsunami events. The hum provided a continuous record, a line drawn through space rather than a series of dots. It allowed scientists to see not just what the density was at specific moments, but how it changed smoothly over time as Voyager moved deeper into the interstellar medium. What they found was that the density was not constant. It fluctuated gently over distances of a few astronomical units, small variations but real, suggesting that the interstellar medium in Voyager's neighbourhood has subtle structures, regions where the plasma is slightly denser or slightly thinner than the average. These variations might be caused by pressure waves from the heliosphere, ripples propagating outward from the sun's interaction with the interstellar medium, or they might be pre-existing features of the interstellar medium itself, wrinkles in the fabric of the galaxy that were there long before our solar system arrived. The hum also behaved in a way that matched observations from a completely different environment. In Earth's ionosphere, the thin layer of charged particles in our upper atmosphere, a similar continuous emission has been detected and is known to track with electron density. The physics is the same. Electrons oscillate at a frequency set by their density, and the oscillation produces a detectable signal. What works in the ionosphere of Earth also works in the interstellar medium of the galaxy. The same physics, operating across scales that differ by billions of miles. There is something quietly beautiful about this. The same basic process that produces a faint hum in the thin air above your head, hundreds of kilometers up in the atmosphere, produces a faint hum in the thin plasma between the stars, billions of kilometers from the nearest planet. The universe, at its most fundamental level, plays the same music everywhere. The instruments are different, the scales are different, the notes are different, but the physics is the same. Voyager continued to listen. The hum continued to play, and as it travelled deeper into the interstellar medium, the pitch changed slightly. The density shifted and the character of the medium evolved in ways that the scientists were still learning to interpret. They were building a map, not of places but of conditions, a weather report from the galaxy, a forecast written one data point at a time, transmitted at the speed of light, received 23 hours later by a dish antenna in the Australian desert. Consider what this means for our understanding of our own place in the galaxy. For all of human history, we have lived inside the heliosphere. Every measurement we have ever taken of the universe beyond it has been indirect. We observe light from distant stars. We detect cosmic rays that have travelled millions of years to reach us. We model the interstellar medium using theory and inference, but we have never, until Voyager directly touched it, we have never measured its temperature, never counted its particles, never listened to its hum. Every observation from inside the heliosphere is like trying to understand the ocean. By watching waves crash on the beach, you can learn a great deal, but you cannot know what the deep water is actually like until you sail out into it. Voyager is our first boat in that deep water, and the ocean, it turns out, is not the flat, featureless expanse that sailors on the shore imagined. It has currents, it has weather, it has regions of calm and regions of turbulence. It has structure that is invisible from the shore, detectable only by instruments placed directly into the water and allowed to drift. The interstellar medium near the Sun is part of what astronomers call the local interstellar cloud, a warm patch of partially ionized gas, roughly 30 light-years across, that our solar system is currently passing through. This cloud has a temperature of about 7,500 Kelvin, and is composed primarily of hydrogen and helium, with traces of heavier elements. It sits within a much larger feature called the local bubble, a cavity roughly 300 light-years across that was carved out of the interstellar medium by a series of supernova explosions over the past 10 to 20 million years. The local bubble is a wound in the galaxy, a region where the normal density of the interstellar medium has been blasted away, leaving a warm, low-density cavity. Our Sun sits near the edge of this cavity, within the smaller, denser local interstellar cloud. Voyager is sampling the local interstellar cloud directly. Every density measurement it takes, every magnetic field reading it transmits, is a direct observation of this environment, and the observations have been consistently surprising. The density is higher than expected in some regions. The magnetic field is oriented in ways models did not predict. The temperature profile at the boundary does not match the most widely used simulations. Each surprise is small on its own. Together they paint a picture of an environment that is more complex and more dynamic than the model suggested. The hum was the baseline, the constant signal against which everything else would be measured, and in 2020, that baseline was interrupted, not by a tsunami, not by a solar event that could be traced and modelled and understood. Something else changed. The magnetic field jumped, the density rose, the hum shifted to a higher pitch and stayed there, and the quiet, persistent music of interstellar space was replaced by something louder, something sustained, something that suggested Voyager had crossed into a region of space that was fundamentally different from the one it had been travelling through for the previous 8 years. The interruption was not dramatic in the way that a movie would stage it. There was no alarm, no flashing light, just a change in the numbers that the scientists who monitor Voyager's data noticed during their routine review. A change that should have been temporary, a change that was not. It is worth dwelling for a moment on what it means to detect a change like this from 15 billion miles away. The data that carries this information is encoded in radio waves broadcast by a transmitter with less power than a refrigerator bulb. Those radio waves spread out as they travel, growing fainter with distance according to the inverse square law, which says that the signal strength drops with the square of the distance from the source. By the time Voyager's signal reaches Earth, it has been travelling for more than 23 hours and has spread across a sphere billions of miles in diameter. The power that actually arrives at the receiving antenna is measured in fractions of a billionth of a watt. Extracting meaningful delta from a signal that faint requires the largest radio dishes on the planet, sophisticated signal processing algorithms, and a level of patience that has no parallel in any other field of science. Every number in Voyager's data stream, every magnetic field measurement, every plasma density reading, every cosmic ray count was pulled from that impossibly faint signal by engineers and scientists who have spent their careers perfecting the art of listening to whispers from the edge of the solar system. When they say the readings change in 2020, when they say the magnetic field jumped and the density rose and the hum shifted pitch, they are reporting a change so subtle that it would be invisible to any instrument less sensitive than the most powerful radio telescopes on Earth. And yet the change is real. It is consistent. It has persisted for years. And it points to something in the interstellar medium that our models did not expect to find. What happened next, and what it means, is where this story shifts from the known to the unknown. From what science has confirmed to what science is still trying to understand. And the region Voyager entered, the structure it appears to have drifted into, is a place where certainty ends and questions begin. The anomaly did not announce itself. There was no sudden break, no moment where the delta lurched from one state to another like a switch being thrown. It was more like walking through a forest and noticing, gradually, that the air has grown warmer. The trees have changed, the soil beneath your feet feels different. You cannot point to the step where it happened, but at some point you realise you are in a different place than where you started. The change happened while you were moving through it, and only in retrospect can you identify the approximate boundary. In 2020, Voyager 1's magnetometer began reporting a sustained increase in the intensity of the interstellar magnetic field. At the same time, the plasma wave subsystem registered a corresponding rise in electron density. Previous events like this had been triggered by pressure waves from the Sun, pulses of energy that originated from coronal mass ejections and travelled outward through the heliosphere and into interstellar space, compressing the plasma and intensifying its magnetic field for a period of weeks or months before dissipating. These events were understood. They were expected. They were, in the context of Voyager's interstellar journey, routine. What was not routine was the duration. The elevated readings did not fade. They persisted through the remainder of 2020 and into 2021, then through 2021 into 2022, then through 2022 into the fall of 2023, when the communications breakdown caused by the corrupted memory chip interrupted the data stream for 6 months. When science data resumed in mid-2024, the readings were still elevated. Voyager, it appeared, had been inside the anomalous region for 4 years, possibly more, with no sign of emergence. The persistence of the signal is what transforms it from an observation into a mystery. A brief spike in magnetic field intensity can be explained by a passing pressure wave. A sustained elevation over years requires a different explanation. Either the pressure wave is enormously large, larger than any previously observed, or Voyager has entered a distinct region of the interstellar medium, a region with intrinsically different properties than the space it was travelling through before. Both possibilities are being taken seriously by the scientific community. Neither has been confirmed. Neither has been ruled out. and the debate between them is one of the most quietly significant conversations happening in space science today. The first possibility, the giant pressure wave, has the advantage of simplicity. We know the sun produces pressure waves. We know those waves propagate into interstellar space. We know they can compress plasma and intensify magnetic fields. All that is required for this explanation to work is for the wave to be larger and longer lasting than any previously recorded. This is not impossible. The sun's activity varies enormously over its 11-year cycle and over longer timescales as well. A particularly powerful series of coronal mass ejections could, in principle, produce a pressure wave of unprecedented scale that would take years to pass a given point in interstellar space. Adam Szabo, the principal investigator for Voyager 1's magnetometer at NASA's Goddard Space Flight Center, described the mechanism clearly. "The source is like a piston," he said. "The sun pushes outward. The heliosphere expands into the interstellar medium. The interstellar plasma is compressed, and the compression propagates outward as a wave. The piston analogy is apt. It captures the mechanical nature of the process, the way solar activity at the source produces physical effects billions of miles downstream. But the piston analogy has limits. A piston produces a single wave that travels outward from the source. The farther you are from the piston, the more the wave should attenuate, losing energy as it spreads across a larger volume of space. Voyager is now roughly 165 astronomical units from the Sun. At that distance, a pressure wave should be significantly weakened. For the wave to maintain the intensity Voyager is measuring over a period of 4 or more years, it would need to have been extraordinarily powerful at its origin, or it would need to be reinforced by subsequent waves that happen to arrive in close succession. Both are possible, but neither is certain, and the models that attempt to predict the behaviour of solar pressure waves at these distances are constrained by the fact that Voyager is the only instrument we have ever had in interstellar space. There is nothing to calibrate against. There is no second opinion. The second possibility is the one that Adam Szabo himself has proposed, and that a growing number of researchers find compelling. He suggests that Voyager may have entered a small cloud of ancient interstellar plasma, a discrete region of the interstellar medium with its own magnetic field and its own density characteristics, distinct from the surrounding material, the way a warm eddy in a cold ocean is distinct from the water around it. This cloud, if it exists, would not be of solar origin. It would be a pre-existing feature of the interstellar medium, a remnant of some earlier astrophysical process. Perhaps it was ejected by a dying star, a cloud of enriched plasma blown into the galaxy by a stellar wind or a supernova shockwave, now drifting through the interstellar medium and carrying with it the magnetic field of whatever star or star-forming region produced it. Perhaps it is a density fluctuation in the local interstellar cloud, a wrinkle in the fabric of the gas cloud that our solar system is passing through, too small to detect from a distance, but large enough to encompass Voyager's position for years. If Szabo's theory is correct, Voyager is travelling through a genuine structure in interstellar space, not a structure in the sense of a solid object, in the sense of a distinct region with defined properties, bounded by transitions where those properties change, a feature of the landscape, a cloud within a cloud, carrying the signature of processes that occurred long before our sun existed. The phrase "truly make it a huge area" appears in Szabo's description of what confirmation would mean. If Voyager is still inside the cloud after 6 months of silence, he said, referring to the 2023 communications blackout, that would suggest the cloud is genuinely enormous, potentially tens or even hundreds of astronomical units across. That would make it a significant feature of the local interstellar medium, large enough to be scientifically meaningful, and potentially large enough to be detected by future missions or remote observations. A third possibility lingers at the margins of the debate, less widely endorsed but not dismissed. Some scientists have questioned whether Voyager has truly left the heliosphere at all. The heliopause, as Voyager's own data showed, is not a clean boundary. It is messy, dynamic, permeable. The magnetic field did not change direction at the crossing. What if the crossing itself was not complete? What if the heliosphere extends farther than the 2012 crossing suggested? And what Voyager is measuring now is not interstellar structure, but a previously unknown outer layer of the Sun's influence. This idea is harder to reconcile with the particle data, which showed a clear dramatic shift from solar-dominated to galactic-dominated cosmic rays at the 2012 crossing. But the fact that the magnetic field refused to cooperate leaves a thread of uncertainty that some researchers continue to pull on. The boundary between the heliosphere and interstellar space may not be as well defined as the 2013 announcement implied. There may be layers beyond the layers, transitions beyond the transitions, a series of nested boundaries rather than a single clean edge. What all three theories share is an acknowledgement that what Voyager is measuring does not match predictions. The models that scientists built to describe the interstellar medium near the Sun did not include a region of elevated density and magnetic field intensity at Voyager's current position. Whether that region is a solar pressure wave, an ancient plasma cloud, or an unknown extension of the heliosphere, it was not anticipated. And unanticipated findings are the engine of scientific progress. They are the data points that force models to evolve, that push understanding past its current boundaries, that reveal the difference between what we think we know and what is actually out there. The 2023 communications crisis added an agonizing dimension to the uncertainty. For 6 months, Voyager was inside the anomalous region, but unable to transmit coherent data. Those 6 months of lost measurements represent a gap in the record that can never be recovered. Whatever the magnetic field and plasma density were doing during that period is gone, unrecorded, known only to the universe and to a spacecraft that has no capacity to remember what it measured, but failed to transmit. When the data resumed, the scientists did not celebrate publicly. They went back to work. They compared the new readings to the pre-blackout readings. They looked for changes, for trends, for any sign that the anomaly was weakening or evolving. They fed the numbers into models and ran simulations and debated interpretations in teleconferences and journal submissions. The work is ongoing. It will continue for as long as Voyager's instruments keep functioning, which by the most optimistic estimates is another 2 to 5 years. 2 to 5 years to answer a question that touches the fundamental nature of the space between stars. 2 to 5 years to determine whether the structure Voyager drifted into is a passing wave or a permanent feature of the interstellar landscape. 2 to 5 years before the instruments fall silent and the data stops and the question, if it remains unanswered, joins the long list of mysteries that science has identified but not yet resolved. The clock is running, and the hum continues. But there is one more dimension to this mystery that is worth exploring before we move on. Whatever Voyager has drifted into, it got there by accident. The spacecraft was not aimed at this region. It was not sent to investigate a known feature. It was simply travelling in a straight line, at constant speed, through what was assumed to be a relatively featureless environment, and it happened to encounter something unexpected. This raises an obvious question. If one spacecraft travelling along one trajectory stumbled upon a structure within a few years of entering interstellar space, how many other structures are out there that no instrument has ever passed through? The answer, almost certainly, is many. The interstellar medium is vast. Voyager has sampled an infinitesimally thin thread of it, a single line drawn through a volume of space that extends in every direction for light years. The probability that this single thread would pass through something unusual is, on the face of it, small, which means either Voyager was extraordinarily lucky, or features like the one it detected are not rare. If the interstellar medium is filled with density fluctuations and magnetic field variations at the scales Voyager can detect, then these structures may be a normal feature of the environment rather than an anomaly. What Voyager found may not be unusual at all. It may simply be the first one we have ever directly observed, because it is the first time we have ever had an instrument in a position to observe one. This reframing matters. It shifts the question from what is this specific thing to what does the interstellar medium look like at small scales. And the answer to that broader question has implications for everything from star formation to cosmic ray propagation to the long-term evolution of the heliosphere. If the interstellar medium is smoother than we think, structures like Voyager's anomaly are genuinely rare and need special explanations. If the medium is rougher than we think, with small-scale features everywhere, then our models of how cosmic rays travel through the galaxy, how magnetic fields organize themselves between stars, and how the heliosphere interacts with its environment all need to be revised. Voyager cannot answer this question alone. One data point cannot define a population, but it can motivate the search for more data points from future interstellar missions, from improved remote observations, from theoretical work that takes Voyager's findings seriously and asks what they imply about the broader environment. The anomaly is a beginning, not an ending. A door opened, not a door closed. Step back with me now. Pull your attention away from Voyager for a moment, away from the specific readings and the specific debates, and consider the larger picture, because the anomaly Voyager detected is not an isolated puzzle. It is part of a much broader set of questions about the environment our solar system inhabits, the structure we live inside, and how little we truly know about the space that surrounds us. Start with the heliosphere itself. We have spent several chapters describing it as a bubble, which is useful shorthand but not quite accurate. A bubble implies symmetry. It implies a smooth, rounded surface separating one medium from another. The heliosphere is not smooth. It is not necessarily rounded. And its surface, if you can call it that, is constantly shifting, expanding and contracting with the solar cycle, rippled by the pressure of the interstellar medium against it, punctured in some places and reinforced in others by magnetic field interactions that we are only beginning to understand. The shape of the heliosphere has been one of the most contentious debates in heliophysics for more than a decade. The traditional model, developed over decades of theoretical work, showed the heliosphere as a comet-like shape, blunt at the front, where the sun's motion through the interstellar medium compresses the solar wind, and stretched into a long tail at the back, where the solar wind material trails behind like the wake of a ship. This made intuitive sense. The sun is moving through the local interstellar cloud at roughly 23 kilometers per second. Anything moving through a medium at that speed should produce a streamlined shape, compressed at the front and elongated at the rear. But then Cassini arrived at Saturn in 2004 and began detecting energetic neutral atoms coming from the direction of the heliosphere's boundary. These atoms are created when charged particles from the solar wind interact with the interstellar medium, exchanging electrons and becoming neutral atoms that can travel in straight lines through magnetic fields that would otherwise deflect them. By mapping the direction and intensity of these neutral atoms, scientists could construct a rough picture of the heliosphere's boundary. The picture was surprising. The energetic neutral atom signatures were roughly similar from all directions, which some researchers interpreted as evidence that the heliosphere is closer to spherical than comet-shaped. A bubble, not a comet. This interpretation was championed by several research groups and gained significant attention in the scientific press. If correct, it would overturn decades of theoretical work and require a fundamental rethinking of how the heliosphere interacts with the interstellar medium. Others push back hard. The apparent symmetry in the Cassini data, they argued, could be an artifact of the solar cycle. When the sun is active, it heats and compresses the plasma in the outer heliosphere, producing more energetic neutral atoms in all directions. When the sun is quiet, the plasma cools and contracts, producing fewer. The variation in neutral atom signatures that Cassini detected might reflect changes in solar activity over time rather than the actual three-dimensional shape of the heliosphere. Resolving this debate requires data that neither Cassini nor the Voyagers can provide. Two spacecraft crossing the boundary at 2 points cannot define a three-dimensional surface any more than 2 dots on a sheet of paper can define a circle. The hydrogen wall adds another layer of complexity, first detected by the Voyagers in 1992 and confirmed by the New Horizons spacecraft in 2018. The hydrogen wall is a region of compressed interstellar hydrogen that piles up at the leading edge of the heliosphere, where the sun's motion through the interstellar medium pushes the incoming gas into a denser layer. Picture a snowplow moving through fresh snow. The snow piles up in front of the blade, forming a ridge that is denser than the undisturbed snow on either side. The hydrogen wall is that ridge. It is a structure, invisible to the naked eye, detectable only through ultraviolet observations and particle measurements, sitting at the boundary of our solar system and created by the simple fact of our sun's motion through the galaxy. The hydrogen wall is relevant to the anomaly Voyager detected because it demonstrates a principle that applies throughout this story. The interactions between the heliosphere and the interstellar medium create structures, not buildings, not solid objects, but regions with distinct properties, boundaries, densities, temperatures and magnetic field configurations that differ from the surrounding space. The heliosphere is not a passive bubble, sitting still in a static medium. It is a dynamic object moving through a dynamic environment, and the interaction between the two produces features at the boundary and beyond the boundary that are as real and as structured as anything visible to the eye. This means that the space Voyager is travelling through is not featureless. It has geography. It has topology. The interstellar medium near the sun has been shaped by the sun's passage through it, by the heliosphere's pressure against it, and by its own internal dynamics, currents and density fluctuations and magnetic field variations that were there long before our solar system arrived. When Voyager detects an anomalous region of higher density and stronger magnetic field, it is detecting a feature of that geography. A hill in the landscape, a warm spot in the ocean, something that exists because the interstellar medium, like all physical environments, has structure at scales that range from the subatomic to the galactic. Now pull back further, the local interstellar cloud. The warm patch of gas that our solar system is currently passing through is itself embedded in the local bubble. The local bubble is a cavity in the interstellar medium, roughly 300 light-years across, significantly less dense than the surrounding galactic material. It was carved out by supernovae, the explosive deaths of massive stars that occurred within the last 10 to 20 million years. At least 15 supernovae are thought to have contributed to the formation of the local bubble, each one blasting away the interstellar medium in its vicinity and inflating the cavity that we now sit inside. The local bubble is our neighbourhood. It is the cosmic equivalent of the clearing in which our village was built. And it is not permanent. The bubble is expanding, driven by the energy deposited by those ancient supernovae, and its walls, where the blasted out gas has piled up into denser regions, are actively forming new stars. The Sun sits near one edge of the bubble, close to the boundary between the low-density interior and the denser walls. In astronomical terms, we are in a relatively protected environment, shielded not only by the heliosphere, but by the low-density conditions of the local bubble, which reduce the intensity of the interstellar material our heliosphere has to contend with. But this has not always been the case. The Sun moves through the galaxy. Over millions of years it passes through different regions of the interstellar medium, some denser, some thinner, some hotter, some cooler. Evidence from deep-sea sediments on Earth, specifically the presence of iron-60, a radioactive isotope produced by supernovae, suggests that the solar system passed near a supernova explosion roughly 2 to 3 million years ago. The blast wave from that explosion may have compressed the heliosphere dramatically, potentially shrinking it to the point where Earth was partially exposed to the raw interstellar medium. If that happened, the consequences for Earth would have been significant. Without the full protection of the heliosphere, the planet would have been bathed in higher levels of galactic cosmic radiation. That radiation affects atmospheric chemistry, potentially increasing cloud formation and cooling the surface. Some researchers have proposed a connection between these heliospheric compression events and the onset of ice ages, though the evidence is circumstantial, and the chain of causation is long and complex. What this tells us is that the structure Voyager is studying is not merely a scientific curiosity. The heliosphere's interaction with the interstellar medium, the size and shape and permeability of the bubble we live inside, has direct consequences for the planet we live on. Understanding the interstellar medium, understanding its density and magnetic field and how those properties vary from place to place, is not abstract physics. It is a form of planetary self-knowledge. It is the study of the environment our home moves through, the ocean in which our island drifts. Voyager is the first and so far only probe we have ever sent into that ocean. Its measurements, limited as they are by aging instruments and dwindling power, are the only direct data we have. Every reading it transmits is precious. Every month it continues to operate adds to a data set that cannot be replicated by any existing technology. The next mission capable of reaching interstellar space, if one is ever built and launched, would not arrive at the heliopause for decades. In the meantime, Voyager is alone out there, the only instrument humanity possesses that can directly touch the medium between the stars. And the medium is speaking, in hums and field shifts and density changes and unexplained anomalies that persist for years. The question is whether we can understand what it is saying before the instrument that is listening goes quiet for good. There is one more thing worth considering before we move forward. The heliosphere is not eternal. It exists because the Sun exists. When the Sun eventually exhausts its hydrogen fuel, roughly 5 billion years from now, it will swell into a red giant and then collapse into a white dwarf. Its solar wind will cease. The heliosphere will dissipate. The planets, or whatever remains of them, will be exposed directly to the interstellar medium. The bubble will pop, and the space that was once inside the heliosphere will become indistinguishable from the space outside it. This will happen to every star in the galaxy eventually. Every heliosphere, every astrosphere, every bubble of stellar influence will eventually collapse when its parent star dies. The interstellar medium is patient. It was there before the stars, and it will be there after them. It is the default state of the galaxy. The stars and their bubbles are interruptions. Brief, brilliant interruptions in a medium that stretches back to the earliest days of the cosmos and will continue long after the last star is burned out. Voyager is travelling through that medium now. It is touching the default state of the galaxy. It is measuring the environment that existed before our Sun formed, and that will exist after our Sun is gone. There is something profound about that, something that goes beyond the specific measurements and the specific anomalies and the specific debates about pressure waves and plasma clouds. Voyager, built by a species that lives inside a bubble, has reached the space outside the bubble and discovered that outside is not nothing. Outside has properties, outside has structure, outside has a hum that has been playing since before the bubble existed, and that will continue playing long after the bubble is gone. Let's think about what surrounds us. Not the air, not the atmosphere, not even the solar system. Think about what lies beyond all of that, in the spaces between the stars, filling the galaxy like water fills the cracks between stones. The interstellar medium is not one thing, it is many things, layered and interpenetrating, existing simultaneously in the same volume of space. There are atoms of hydrogen and helium, the lightest and most abundant elements in the universe, drifting through the void at density so low that you could travel for thousands of miles and encounter only a handful of particles. There are dust grains, microscopic fragments of carbon and silicon and iron, formed in the outer layers of dying stars and blown into space by stellar winds. There are cosmic rays, individual protons and atomic nuclei, accelerated to nearly the speed of light by supernova shockwaves, carrying more energy in a single particle than a tennis ball served by a professional athlete. And there are magnetic fields, threading through all of it, shaping the paths of charged particles, confining some and redirecting others, forming a vast invisible web of electromagnetic influence that stretches across the entire galaxy. All of this material has a history. None of it is primordial in the strict sense. The hydrogen and helium were created in the first few minutes after the Big Bang, forged in the extreme temperatures of the infant universe, but the heavier elements, the carbon and oxygen and iron, were made inside stars. Every atom of iron in the interstellar medium was fused in the core of a massive star and released into the galaxy when that star exploded. Every grain of cosmic dust was condensed in the cooling outflows of a red giant or the expanding debris field of a supernova. The interstellar medium is the graveyard and the nursery of stars. It contains the ashes of the dead and the raw material for the newborn. Every new star that ignites does so from material that has been recycled through previous generations of stars, each generation enriching the medium with heavier elements, each death contributing to the chemical complexity of the next birth. Voyager is drifting through this medium now. The particles that strike its instruments, the magnetic fields that its magnetometer measures, the plasma that its wave detector listens to, all of it carries information about the history of the galaxy. A cosmic ray that reaches Voyager's detector may have been accelerated by a supernova that exploded 10 million years ago in a region of the galaxy thousands of light years away. The magnetic field Voyager measures may have been shaped by the same supernova, or by a different one, or by the cumulative effect of thousands of stellar events over millions of years. The interstellar medium is a palimpsest, a document written and overwritten by successive generations of stellar activity, each layer partially obscuring and partially preserving the ones beneath it. Reading this document is one of the great challenges of modern astrophysics. From inside the heliosphere, we can study the interstellar medium only indirectly, through the light it absorbs or emits, through the cosmic rays it produces and deflects, through the gravitational and magnetic effects it exerts on nearby stars. These indirect methods are powerful but limited. They give us averages and approximations. They tell us what the interstellar medium is like in general, across large volumes. They cannot tell us what it is like in the specific neighbourhood that Voyager is travelling through, at the specific scales that Voyager can resolve. That is what makes Voyager's measurements so valuable. They are specific, they are local, they are direct. When Voyager measures a plasma density of 0.12 electrons per cubic centimetre, that is not an average over a region of space. It is the density at the spacecraft's exact location at that exact moment. When it measures a magnetic field strength of 0.5 nanotsler, that is the field at its position, not a modelled estimate. These measurements are like core samples drilled into the Earth. Each one is narrow, limited to a single point, but it tells you exactly what is there, not what a model says should be there. The specific neighbourhood Voyager is travelling through has some features worth describing. The Sun sits near the edge of the local interstellar cloud, a patch of warm, partially ionised gas with a temperature around 7,500 Kelvin. This cloud is about 30 light years across, and is one of several such clouds in the immediate vicinity of the Sun. The clouds are not static. They move relative to the Sun and relative to each other, drifting through the local bubble at speeds of tens of kilometers per second. The Sun itself is moving through the local interstellar cloud at about 26 kilometers per second, ploughing through the gas like a ship through water. Some researchers have suggested that the Sun is near the edge of the local interstellar cloud and may be approaching a transition to a different cloud or to the lower density interior of the local bubble. If the Sun were to leave the local interstellar cloud and enter a region of significantly lower density, the heliosphere would expand dramatically, pushing the heliopause farther from the Sun. If it entered a region of significantly higher density, the heliosphere would contract, potentially exposing the outer planets or even the inner solar system to higher levels of galactic cosmic radiation. These transitions would not happen overnight. The Sun's motion through the interstellar medium is measured in light years per million years. A cloud boundary that is 10 light years away would not be reached for hundreds of thousands of years. But in geological time, these transitions are frequent. The Sun has passed through multiple interstellar environments over the course of its 4.5 billion year life, and each transition has altered the heliosphere and, indirectly, the conditions on every planet within it. This is the context in which Voyager's anomaly sits. The interstellar medium is not a blank canvas, it is a landscape, shaped by billions of years of stellar activity, filled with clouds and bubbles and density fluctuations and magnetic fields that interact with each other and with the heliospheres of the stars that move through them. When Voyager detects a region of higher density and stronger magnetic field, it is detecting one feature of this landscape, one hill, one valley, one warm pool in a vast and varied ocean. The question of what produced that feature remains open. Was it sculpted by a pressure wave from our own Sun, a recent event in astronomical terms, still propagating outward from the heliosphere into the surrounding medium? Was it a pre-existing feature, a density fluctuation in the local interstellar cloud that has been drifting through the galaxy for millions of years, carrying the magnetic signature of whatever produced it? Was it shaped by a distant supernova, a shock wave that passed through this region of space long ago and left behind a compressed layer of plasma and enhanced magnetic field? Each of these possibilities tells a different story about the environment we live in. The first tells us that the Sun's influence extends farther into interstellar space than we thought. The second tells us that the interstellar medium has structure at scale smaller than we previously appreciated. The third tells us that the galaxy's violent past has left imprints in the space near our solar system that we are only now capable of detecting. All three are interesting. All three are plausible. All three, if confirmed, would deepen our understanding of the universe in meaningful ways. And all three remain unresolved because Voyager, the only instrument that can test them, is running out of time. The cosmic rays that Voyager detects are worth a moment of reflection on their own. Each one is a traveller, an individual proton or atomic nucleus that was torn from a star by the violence of a supernova explosion and hurled into the galaxy at nearly the speed of light. These particles travel for millions of years, deflected and redirected by the magnetic fields of the interstellar medium, bouncing through the galaxy like balls in an impossibly vast pinball machine. By the time one of them strikes Voyager's cosmic ray detector, it has travelled a distance that makes Voyager's own journey look trivial. It has crossed the galaxy. It has passed through clouds and voids and magnetic field structures that no human instrument has ever mapped. It carries in its energy and its trajectory a record of every magnetic field it has passed through and every shock wave that has accelerated it. Voyager counts these particles. It measures their energy. It records the direction they come from. And from these measurements, scientists can learn about the conditions of interstellar space, not just at Voyager's position, but throughout the broader region that these cosmic rays have travelled through. The cosmic ray data is a form of remote sensing, using particles instead of light to probe the galaxy's structure. In interstellar space, the cosmic ray intensity is higher than inside the heliosphere. This was expected. The heliosphere shields the solar system from more than 70% of galactic cosmic radiation. Beyond the heliopause, the full intensity of the galactic cosmic ray flux is present, unshielded, a constant rain of high-energy particles streaming through the interstellar medium from all directions. But the intensity is not perfectly constant. It fluctuates with regions of slightly higher and slightly lower intensity that correspond to variations in the magnetic field and plasma density of the surrounding medium. These fluctuations add to the picture of an interstellar medium that is not smooth and not static, but textured and dynamic, full of small-scale structure that Voyager is mapping for the first time. Each of these observations, the hum, the anomaly, the cosmic ray fluctuations, the magnetic field alignment, contributes a pixel to a picture that is still too incomplete to interpret with confidence. We are looking at a landscape through a keyhole, seeing fragments without the context that would make them meaningful. And the keyhole is closing. Voyager's power is fading. Its instruments will fall silent within a few years. The picture, incomplete as it is the best we will have for decades. What we do with that picture, what theories we build from it, and what questions we carry forward into the era when new instruments might finally reach interstellar space, depends on what happens in the time Voyager has left. Every day it continues to operate is a gift. Every measurement is a line drawn on a map that no one else has ever drawn. The map is fragmentary. The map is uncertain, but it exists, and it shows us a universe that is stranger and more structured and more full of surprises than the one we imagined before a small machine with a golden record drifted into it. And that map, incomplete as it is, has already changed something fundamental about how we understand our place in the galaxy. Before Voyager, the space between the stars was an abstraction, a void defined by absence, a gap between the things that mattered. Now it is a place, a real, measurable, structured place, with properties and dynamics and features that affect our solar system and everything within it. The interstellar medium is not the background. It is the medium in which our existence is embedded. It is the water in which our island floats. And Voyager, with its aging instruments and its fading power and its golden record turning silently in the dark, is the first thing we have ever sent out to learn what that water is like. What it has found so far is only the beginning, a few years of data from a single trajectory through a medium that extends for thousands of light years in every direction. A handful of measurements from instruments designed half a century ago for a completely different purpose. A whisper from the edge of what is knowable, carried home on a signal so faint that it takes the largest radio dishes on Earth to hear it. But beginnings matter. They set directions, they establish what is possible. And this beginning, this first tentative exploration of the space between stars, has shown us that what lies beyond our bubble is not emptiness. It is an environment as real and as complex as any we have ever studied. An environment that has been shaping our solar system for billions of years and will continue to shape it for billions more. An environment with secrets that Voyager has only begun to uncover, and that future missions, if we have the will to build them, may one day explore in ways that Voyager's designers could not have dreamed of. The power is fading. It has been fading since the day Voyager launched, a slow, predictable decline built into the physics of its fuel. Plutonium-238 decays. That is what it does. It sheds alpha particles and heat with a half-life of 87.7 years, meaning that every 87.7 years, half of the plutonium that remains will have transformed into something else, something that no longer generates the heat that Voyager converts into electricity. The decline is not sudden. It is gradual, relentless, and precisely calculable. The engineers who designed the power system knew exactly how much electricity would be available in 2025, in 2030, in 2050. They knew because the physics is exact. There is no uncertainty in the rate of radioactive decay. There is only certainty that the power will diminish, and that at some point there will not be enough left to run anything at all. As of the most recent engineering assessments, Voyager 1's 3 radioisotope thermoelectric generators produce roughly 220 watts of electrical power. That is less than half of what they produced at launch. It is enough to power a few small light bulbs. It is enough with careful management to keep the spacecraft's essential systems running and 4 scientific instruments operating. But the margin is thin. Every watt matters, and every year 4 more watts disappear. The mission team has been managing this decline for decades, with a combination of engineering creativity and difficult choices. Heaters have been shut off, instruments have been powered down, subsystems that were built with redundant backups have been reduced to single-string operation, meaning that if any one component fails, there is no spare to take over. The spacecraft operates now at temperatures that would have alarmed its designers. Components that were rated for specific thermal ranges are functioning below those ranges, surviving on a combination of robust construction and the kind of luck that engineers do not like to rely on but cannot avoid. The choices have become harder as the power has dropped. In 2019, the mission team implemented a revised power management plan that involved shutting down the heater for the cosmic ray subsystem on Voyager 2. The instrument continued to function despite operating at a temperature colder than it had ever been tested at. Similar choices have been made for Voyager 1. Each time the team weighs the scientific value of keeping an instrument running against the risk that running it will draw power from other systems and accelerate the overall decline. These are not abstract decisions. They are trade-offs between specific scientific capabilities, and each one narrows the range of questions that Voyager can answer. The 4 instruments still operating on Voyager 1 are the magnetometer, the plasma wave subsystem, the cosmic ray subsystem, and the low energy charged particle instrument. Together, they provide a minimum but meaningful picture of the interstellar environment. The magnetometer measures the strength and direction of the magnetic field. The plasma wave subsystem listens to the electrical oscillations of the surrounding plasma. The cosmic ray subsystem counts high energy particles from across the galaxy. The low energy charged particle instrument detects particles at lower energies, filling in the gap between the plasma detector and the cosmic ray detector. These are the instruments that detected the anomaly. These are the instruments that hear the hum. These are the instruments that will continue to report on the properties of interstellar space for as long as they have power to operate. The mission team's priority is to keep them running as long as physically possible. The team is hoping to maintain the magnetometer and plasma wave subsystem on both Voyagers through at least 2027, the 50th anniversary of the launch. After that, further shutdowns will likely be necessary, and the scientific capability of the spacecraft will diminish with each one. There is another constraint, less often discussed but equally consequential: communication. Voyager 1 transmits its data using a radio transmitter that broadcasts at a power of about 23 watts, roughly the power of a dim light bulb, through a high-gain antenna 3.7 meters across. That signal, spreading out over the distance between Voyager and Earth, is extraordinarily faint by the time it reaches us. Detecting it requires the largest and most sensitive radio antennas on the planet, part of NASA's Deep Space Network. One antenna in particular is critical. Deep Space Station 43, a 70-meter dish located near Canberra, Australia, is the only antenna in the Deep Space Network capable of sending commands to the Voyager spacecraft. Other antennas can listen to Voyager's transmissions, but only DSS-43 can talk back. And between May 2025 and February 2026, DSS-43 was taken offline for major upgrades to its aging infrastructure, with only limited operational windows in August and December 2025. During the months when DSS-43 was unavailable, the team could receive data from Voyager, but could not send commands. If something went wrong with the spacecraft during that window, if a fault protection system triggered unexpectedly, or an instrument began behaving anomalously, the team would be unable to respond until the antenna was restored. This is the fragility of the mission at this stage. Voyager is not just old and low on power. It is at the end of the longest supply line in history. The communication link that keeps it connected to Earth is maintained by ground infrastructure that is itself aging and in need of repair. The team that manages the mission is smaller than it has ever been, because budgets for a 48-year-old mission are difficult to justify against the competing demands of newer programs. The institutional knowledge required to operate a spacecraft built with 1970s technology is held by a shrinking number of people, some of whom have been with the mission since before launch. And yet the mission continues. It continues because the data it produces cannot be obtained any other way. No other instrument exists in interstellar space. No other instrument will reach interstellar space for decades. The next proposed interstellar probe mission, if funded and launched on the most optimistic timeline, would not reach the heliopause until roughly the 2060s or 2070s. In the meantime, Voyager is the only source of direct interstellar data that humanity possesses. Turning it off early, or allowing it to fail through insufficient support, would not just end a mission, it would close a window that cannot be reopened for a generation. In October 2024, the mission experienced another scare. NASA had turned on one of Voyager 1's heaters on October 16th, and the spacecraft's fault protection system responded by lowering the transmission rate. Engineers found the signal, but on October 19th, the fault protection system triggered again and switched the spacecraft from its primary X-band radio transmitter to a backup S-band transmitter that had not been used since 1981. The S-band signal was weaker and carried less data, but it was there. The team worked through the problem, reactivated the X-band transmitter, and resumed normal data collection by mid-November. The incident was a reminder that at Voyager's age, every system is a single point of failure, and every anomaly could be the last. The 2023 crisis was worse. The corrupted memory chip in the flight data subsystem rendered all of Voyager 1's transmissions unintelligible for 6 months. The team's fix, rewriting the software to route data around the damaged chip, was described by multiple commentators as one of the most impressive remote engineering feats in the history of space exploration. The round-trip communication delay of nearly 2 days meant that every diagnostic step, Every test command, every software upload took days instead of minutes. The engineers were debugging a 50-year-old computer from 15 billion miles away, and they did it. Not quickly, not easily, but they did it. These crises will continue. The spacecraft is old, its components are degrading, its power is declining. Each year that passes increases the probability that a failure will occur from which recovery is impossible. The team knows this. They operate with the quiet, steady competence of people who have spent decades managing a system that is always one malfunction away from silence. They do not dramatize. They do not panic. They plan and they respond, and they keep the data flowing for as long as the universe allows. Let's talk about what happens when the data stops. Voyager 1 will not cease to exist when its instruments fall silent. It will still be there, in interstellar space, moving at 38,000 miles per hour, carrying the golden record, carrying the memory of every photograph it took and every measurement it made, even though it will no longer be able to share them. It will become an artifact. A time capsule sealed not by a lid but by the silence of depleted plutonium and darkened circuits. It will continue on its current trajectory, heading generally in the direction of the constellation Camelopardalis. In approximately 40,000 years, it will pass within about 1.6 light years of a star called Gliese 445, a small red dwarf that is currently about 17 light years from Earth. Voyager will not stop at Gliese 445. It will not orbit it. It will pass by, carried by its own momentum, and continue onward. There is nothing in its path for millions of years that would slow it down or alter its course. It will drift through the galaxy on a trajectory that is, for all practical purposes, permanent. The golden record, sealed in its aluminum cover and bolted to the spacecraft's body, is designed to endure. In the vacuum of interstellar space, there is no air to corrode the metal, no water to rust the surface, no biological agents to degrade the organic materials. The primary threat to the record is cosmic ray bombardment, high-energy particles that can damage the surface over extremely long timescales. Estimates suggest that the record could remain readable for hundreds of millions of years, possibly longer. The spacecraft itself, made of aluminum and other metals, will endure for even longer. Billions of years, potentially, drifting through the galaxy as a silent monument to the civilization that built it. Nobody will be listening. The record will play for no one, assuming no one finds it. The probability of interception is effectively zero, over any timescale that a human mind can meaningfully consider. The galaxy is vast. The spaces between stars are enormous. A single spacecraft the size of a small car, carrying no beacon, emitting no signal, is for all practical purposes invisible. Even if intelligent life exists elsewhere in the galaxy, the chances of it encountering Voyager are vanishingly small. Sagan knew this. He included the record anyway, not because he believed it would be found, but because the act of making it, of choosing the music and the greetings and the images and the sounds, was itself the point. The record is a portrait of a species that looked up at the stars and wondered what was there, a species that built a machine to go and see, a species that, knowing the odds of the message being received were nearly zero, sent it anyway, because not sending it would have been a concession to indifference that they were not willing to make. And now, in what may be the final years of Voyager's active life, the machine that carries that message is also carrying data about a mystery it stumbled into by accident. A region of interstellar space with properties that do not match any model. A structure or a wave or a cloud, or something for which we may need a new word. Something that exists in the space between stars and that we did not know was there, until a 50-year-old spacecraft drifted into it and noticed that the numbers had changed. There is a symmetry to this that is hard to ignore. Voyager was built to explore the known, the planets that we could see through telescopes and whose positions we could calculate with precision. It did that brilliantly. Then it was asked to explore the boundary, the heliosphere's edge, the place where the known meets the unknown. It did that too, with results that overturned decades of theoretical work. And now, in its final years, it is exploring something that no one asked it to explore, a feature of the interstellar medium that was not predicted, not sought, not even imagined. The greatest discoveries are often the ones you did not go looking for, the ones that find you while you are on your way somewhere else. The anomaly may be explained in time. Future analysis of Voyager's remaining data, combined with new observations from ground-based and space-based instruments, may eventually determine whether the elevated readings are caused by a solar pressure wave, an ancient plasma cloud, or something else entirely. The answer, when it comes, will tell us something important about the environment our solar system moves through and about the forces that have shaped the interstellar medium over billions of years. Or the anomaly may remain unresolved. Voyager's instruments may fail before enough data has been collected to distinguish between the competing explanations. The measurements may be tantalizingly suggestive, but ultimately inconclusive, joining the long list of scientific questions that are identified, explored, and then left open, because the tools available were not quite sufficient to close them. This would not be a failure. It would be a signpost, a marker that says here is something interesting, and here is where we ran out of capacity to study it. Come back with better instruments and finish what we started. In November 2026, Voyager 1 will reach a distance of 1 light day from Earth. 1 light day. The distance that light travelling at the fastest speed the universe permits covers in 24 hours. At that point, a signal sent from Earth will take a full day to reach the spacecraft, and a response will take another full day to return. A single exchange of information will span 2 days. A conversation will be measured in weeks. The distance will continue to grow, and the delay will continue to lengthen, and eventually the signal will be too faint to detect, and the conversation will end. But the machine will still be there, drifting, silent, carrying a golden record in the memory of a world it left behind half a century ago, carrying the last measurements of a mysterious region of interstellar space that it entered by chance, and studied with instruments that were never designed for the task, carrying the evidence that the space between stars is not empty, not featureless, not the blank void that generations of astronomers once assumed. It is an environment. It has structure. It has weather. It has features that we are only beginning to detect, let alone understand. If you are still listening, you have travelled a long way, from a launch pad in Florida to the moons of Jupiter, from the rings of Saturn to the pale blue dot of Earth, seen from 6 billion kilometres away, through the termination shock and the heliosheath and the heliopause, across the boundary of the sun's influence and into the true space between stars, through the hum of the interstellar medium and into the anomaly that no one predicted. And now, to the edge of what the mission can give us, the last years of a spacecraft that has done more than anyone who built it ever imagined. Voyager did not go looking for the structure it found. It went looking for the planets. When it finished with the planets, it went looking for the edge of the heliosphere. When it found the edge, it crossed it. And on the other side, in the cold, ancient, dimly understood medium between the stars, it encountered something that the models had not prepared us for. A region of space that is denser and more magnetically intense than the surrounding medium. A feature of the interstellar landscape that may be a relic of our own sun's activity, or a relic of a star that died before our sun was born, or something that belongs to a category we have not yet defined? The answer matters. It matters for our understanding of the heliosphere and its interaction with the galaxy. It matters for our understanding of the interstellar medium and the forces that shape it. It matters in a distant but real way for our understanding of the conditions that have influenced our own planet over millions of years. And it matters because it is the kind of question that defines a species. Not a species that has the answers, but a species that asks, that builds, that sends things into the dark to see what is there, that listens patiently for decades to the faintest whisper from the farthest machine and tries to understand what it means. The signal will fade, that is certain. The plutonium will decay. The instruments will shut down one by one. The transmitter will fall silent, and Voyager will drift on, carrying a golden record in a story that is not yet finished, into a galaxy that is larger and stranger and more full of structure than anyone knew when the machine was launched on a warm September morning in 1977. Somewhere out there in the space between the stars, a hum continues, a faint vibration in the plasma produced by electrons that have been oscillating since before the Earth existed. Voyager heard it. Voyager measured it. Voyager sent the measurement home, across 15 billion miles of emptiness at the speed of light, to a dish antenna in the Australian desert, where a small team of scientists received it and added it to the longest and loneliest data set in the history of science. The hum does not know it has been heard. The plasma does not know it has been measured. The universe is not aware that a small machine from a small planet is drifting through it, listening. But we know. We know because we built the thing that listens. We know because we chose to keep listening even when the signal grew faint, even when the budgets grew thin, even when newer and shinier missions competed for attention and resources. We chose to keep the old machine running. We chose to keep asking the question. We chose, in the quietest and most persistent way a species can choose, to not stop wondering what lies just beyond the edge of what we know.